structural engineer, and so I'm here presenting work that my student Camila Lopez Ruiz has done, largely with Michaela Largent and Dr. Jenny Watson-Lamprey. So there are seismologists who did sort of the first half of the study. So Dr. Watson-Lamprey and I were chatting, and she was very interested in this topic about how if you start getting larger ground motions, especially talking about larger epsilons beyond the median predicted ground motions, that is actually negatively correlated with the durations that you would expect for these ground motions. And I said, well, as a structural engineer, I think that's interesting because we like to do these incremental dynamic analyses, and we pick larger and larger suites of motions intensity-wise, but we don't scale down the durations for those, or select ground motions with smaller durations for those. And so if you're seeing a lot of damage, nonlinear behavior, that would have an effect on the responses. So we are looking at this for two bridges at two different sites in California. One is a major toll bridge. You can see it's based on the Coronado Bridge in Southern California, and a typical highway overpass in Northern California. And focusing on the hazard analysis, looking at that correlation between intensity and duration, as well as what effect does that have on your damage predictions for your toll bridge and highway bridge. So at Slate Geotech, they looked at the correlations using the intra-event residuals from 4 NGA West 2 ground motion prediction equations. And they used 3 duration prediction equations, Abrahamson and Silva from 1986, Baumer et al., and Afshari and Stewart. And you can see the results down in the bottom for the 3. This is for the ASK ground motion prediction equation, and you can see they all have negative correlations. Abrahamson and Silva and Baumer et al. Have smaller correlations than what you see for Afshari and Stewart. So you can see for Afshari and Stewart, in the short period range particularly, there is a large, so negative 0.5 correlation between the intensity and the duration. So using this, we sort of kept on going with this larger one so that we could see what the sort of worst case scenario would be on the effects of our response. And this is just sort of an aggregate of that. Again, this is normalized correlation coefficients. So the correlation coefficient average was about negative 0.4, so it would be multiplying this. So you can see that the correlation is the strongest in the short period areas, and if you have a structure that's maybe over 2 seconds, it's not a big significant correlation, so it's probably not going to affect very long period bridges, very long period buildings for that. But if you're looking at the shorter systems, then you'll have that strong correlation. So to do the analysis, we did an incremental dynamic analysis of these 2 bridges. We started with sort of a basic, like the most generic way you could do an IDA. We chose one suite of 11 ground motions based on the 2,475-year spectrum. And we used those same ground motions, and we amplitude scaled them up, so just multiplied them. We didn't change the ground motions, we didn't change the durations at all. Then the other way we did is we chose an initial spectrum of ground motions that was all based on the correct duration using our correlation equation. And then we chose a new suite of ground motions for every increment. So new suite of of ground motions for 2, 2.5, 3, etc. We calculated, at Slate they calculated the epsilon value that was associated with each one of those response spectra, and then they found the mean duration using the Afshari and Stewart correlation equation, and with those mean durations were all accounted for. So just as a reminder, we're really focusing on that epsilon. So if you are right by a fault that's having frequent large events, then this is probably not affecting you as much, but if you have these infrequent large events that are large deviations from the median, so if you're looking at this, so this is, I think, our Coronado Bridge location. You can see blue is our median prediction, then I have 2475 is an epsilon of 0.68 above that, and then if we scale factor that up to 4.5, we have an epsilon of 2.75, so rather large epsilons for choosing our ground motions. So for our major toll bridge, we were using a model based on the Coronado Bridge. This is a bridge that sort of has half isolation up some of its increasingly piers of increasing heights. And it's right by the Rose Canyon Fault Zone, so very near fault. And we have isolators there, as I mentioned. And here's our hazard characterizations for our different return periods. We're focusing mostly based on the 2475 year. And so this is near fault, large magnitudes, DS30 of 300 meters per second, and a period of 1.6 seconds. So it's interesting because this is getting out there. It's a longer period, so you'd expect to see not as much effect from the correlation, but you'll see in the results that it still is there, even though we're at 1.6 seconds. So the mean duration, if you do not include any correlation for this, the prediction is about 13 seconds. But if you look at the 2475, when you consider that epsilon, you reduce that to 2.4 seconds, and then if you now scale up your ground motion, the sort of mean duration that you would expect is 11 seconds. So you're getting almost 2 seconds off of your ground motion. Not huge, again, because we have this longer period structure. It's 1.5 seconds. And so we looked at, here's our model. This is actually a 3D model. We're just looking at the planar view. So we're actually getting the effects. We have linear elastic beam columns for our deck. For our bearings, we have lead rubber bearings that have some degradation with the heating of the lead, because more cycles that you'd expect in a longer ground motion, you get heating and softening in those. Then we have nonlinear beam columns for our columns to get the damage in the column behavior. And we did very simplified abutments. We did rather simplified damage states for these. So this is work based off of University of Nevada, Reno's research into bridge column damage. And we focused on damage state 3 and 5 and used drifts as metrics for the pier damage. And for our bearing damage, we used, we sort of made up our own because there are not sort of validated damage states for isolators. So for, we used this overlapping area method for buckling as the limit state, and we assigned that for damage state 3. This is well known to be highly conservative, so you wouldn't actually expect a bearing to be near failure when you reach that. So this is showing how conservative that line is compared to the experimental tests that we do for these bearings. So for our major damage for the bearing, we assumed that 0 overlapping area, so you have no direct load path from the top to the bottom of the bearing, would be our damage state 5. So that's our damage state 5 there. So we go through and we use that to create fragility curves. This is looking at every single bearing on top of the piers, and so we've now run our IDAs. This is for the non-correlated set of ground motions, and we can from then go through, this is just for the bearings, go through and consolidate this using pretty rudimentary, just sort of worst case, we choose which bearing is the worst damage, and that's sort of setting the bar for that motion. So our tall piers are not having as large of displacements, or sorry, are having much larger displacements because the pier is really driving the motion in these bearings than our shorter piers. So our damage is happening there in our bearings predominantly. And we can aggregate this through to get these fragility curves for damage state 3, and 5, using both the bearings and the piers. And we're using, for this study, we're looking a lot at the medians because, as you know, the dispersion is really dependent on what ground motions you're selected, and really we're looking at one study versus the other. We don't have many of these, so we're just looking at how these medians are shifting. So here are really our results. The dotted lines are the non-correlated suites, and the solid lines are the correlated suites. So you can see that going from having no duration considered to having a correlated duration, you have the shift over to the right, which means you have more capacity, basically, for your bridge. And that's true, too, for damage state 5. Okay? And so you can see the shift of that median is on the order of 27%. And this is for, again, a more flexible bridge where you have less of that correlation. And again, the dispersions that you see on here is really going to be dependent just for this study on the ground motions that were selected. Then we go and look for the typical highway bridge, and we centered that in Northern California and very close to here. And so this is, again, near fault, but the period of this bridge is 0.5 seconds. So much higher correlation, and so you can see that. So the mean duration here would start out at 15.5 if I didn't consider any correlation. If you look at that epsilon, even for the 247